Hello everyone, welcome to this course on reinforced concrete design. We are in week 1 and this is our first lecture. Now, as you all know, in reinforced concrete design, the material that we use is the reinforced concrete, right? So, there are two major components in RCC. As you can see here in this photograph, there are steel rebars used and obviously cement concrete is poured, right? And with time, this cement concrete, which initially has a liquid form as you can see, then it sets and together they form a hard mass, right? So what are the two components? The first one is obviously cement concrete, or we call it concrete. And the second one is steel. So before we start our design of RCC structure, let us quickly go through what are the different components of this concrete and what are the behaviors, stress strain behavior of these two materials so that we can use them in our design, right? So first is cement concrete. Now, cement concrete is a mixture of three different components: cement, then aggregate, and water. Within aggregate, we have two different types of materials used. One is sand and another is gravel. Now, these components are mixed together in certain proportion and then water is added. And the moment water is added, it reacts with the cement and then together they form cement concrete. Now, this proportion of different materials in cement concrete is extremely important because that dictates the strength of the material. We'll come to that point. But before that, when we mix all these components together, initially they form a plastic mass that gradually flows. As you can see here, the concrete is flowing and there is a formwork. Within the formwork, steel rebars are placed and then this concrete is poured and then with time it sets. So initially, cement concrete is a plastic mass. So it is a plastic mass that gradually hardens over time, right? Gradually hardens. Now, if you look at the hardening process of cement concrete, there are three different phases. The first phase, we call it initial phase. And it stays within the first 30 to 60 minutes. So the moment we mix cement, aggregates and and water, then initial 30 to 60 minutes is the first phase. And during this phase, this plastic mass that flows, as you can see here, so it has this flowing characteristics and that helps us to pour concrete and give it a shape of the formwork that we first prepare so that we can construct the structure. Now, once the concrete is poured, then there is an intermediate phase. Now, this intermediate phase stays around 5 to 6 hours. It also depends upon many other factors. For example, sometimes we use additional chemicals with this mix just to accelerate this process or sometimes decelerate also, depending upon the situation. But without those additional materials, chemicals used in concrete, normally the intermediate phase stays around 5 to 6 hours. Now, during this period, what happens? During this period, concrete loses its flowing characteristics. Okay. It is not rock solid, but it actually gets the shape of the formwork and it does not flow. Then comes the final phase. And this final phase is up to 28 days. So from the moment we mix cement, aggregate and water, then we pour the concrete within the formwork to give the proper shape. Within first 5 to 6 hours, there is an initial setting. Then the concrete doesn't flow. With time, chemical reaction between water and cement happens. Because of that reason, concrete gradually gets its strength. And then from day 1 to up to 28 days, if it is properly cured, then at the end of 28 days, we get the proper design strength. Now here you should note that beyond 28 days also concrete gains strength, but that is a very slow process and we normally do not rely on that additional strength beyond 28 days. So in our design, we'll use the strength that the concrete achieves at the end of 28 days with proper curing. Okay, so now why cement concrete in particular is used in building constructions? Cement concrete is very good in compression. And at the same time, it is very weak in tension. So wherever there is a tensile force developed, concrete immediately cracks. And that's the reason we use rebar. Okay. So for tensile strength, we use rebars. And together they form reinforced cement concrete. Now, let us quickly go through what are the different types of cements we used and what are the different characteristics of other components that we have in cement concrete. So first is cement. Now, there are different types of cements available. For example, Portland cement. Then we have high alumina cement. Then we have natural cement. Then we have super sulfate cement. And the list continues. Okay. In our entire course, we'll use this ordinary Portland cement. Okay. All other types of cements are normally used for special purposes. So for the time being, we'll not go into the details of this. We'll only focus on ordinary Portland cement. Now, what are the different components of cements? Let us quickly go through. The first one is lime. Second one is silica. Next is alumina. Then iron oxide, magnesia, then sulfur trioxide, and finally soda and or potash. So these are the different chemicals or chemical compounds used to prepare cement. Let us just quickly go through the different components. So iron oxide, so Fe2O3, then magnesium oxide, MgO, Iron oxide we have already mentioned. Then sulfur trioxide, S3, and then Na2O plus K2. Now these are the different compounds. They are mixed together and there is a specific process of heat treatment at very high temperature, and then once they are mixed and properly processed, they form tricalcium silicate, then dicalcium silicate, then tricalcium aluminate, and then tetracalcium aluminoferrite. So these are the different compounds of cement, right? And in fact, these are the compounds that react with water, develops heat of hydration, and once it dries, it forms a very solid mass. So we start with these compounds, they are mixed together at very high temperature and then pulverized, and then these are the compounds that forms cement. Now out of this tetracalcium aluminoferrite, it is there, but it doesn't participate in heat of hydration. But this tricalcium silicate, dicalcium silicate, and tricalcium aluminate, these are the three main ingredients that react with water, and then they offer the adhesive strength, right? Now obviously the amount of water and quality of water is also very important, that will come into after some time. So first we have cement, and we have already gone through the different components of cements. So let us see what are the different aggregates that we use in cement concretes. Now there are two different types of aggregates mainly used. One is called coarse aggregate and another is fine aggregate. It is actually called sand, and the coarse aggregate is called gravel. Now, how do you differentiate coarse and fine aggregate? Coarse aggregate are those with a size of 4.75 millimeter or above. And if it is less than 4.75 millimeter, obviously we call it fine aggregate, and which is sand. Now there are further gradations of both of them. So they must be well graded. The idea is we have, say, bigger gravels, and then we have smaller gravels, and then in between gravels we have sand, and then finally we have cement slurry, cement mixed with water. They form actually the binding material between these different gravels or different aggregates. Together they form cement concrete. Okay, so that's the logic, and that's the reason it must be very well graded, and there are specific codal provisions for this grading of gravels, and the code is IS 383 1970. We'll obviously not go into the details of these codal provisions, their meaning, their guidelines, because this course is not on materials. But obviously, as a designer, we must know the different components and ingredients of the material that we are going to use. And that's the reason we are going through these different components and their properties. Now, when we deal with aggregates, and for that matter, all the components, there are different types of tests also specified. For aggregates, we have two main tests that we do to check the adequacy of those aggregates. The first one is crushing strength or crushing value, and the second one is impact test. And there are a few more tests are there, but these are the two main tests that we carry out to check the quality of this aggregate. Now, as I said, we will not go into the details of these tests in this course. That is not our objective. But those who will deal with materials, which is concrete here, then they must go through the details of this and what are their meanings, what are the procedures. Now, for the time being, what are the different properties that we should be worried when we design a reinforced concrete structure? These are as follows. So we have first strength, then size, then particle shape, physical and chemical stability at high temperature, then coefficient of thermal expansion, and finally, obviously, cost. Now, out of that, we can easily appreciate the strength and size because, as I said, the first thing that dictates what are the type of aggregates that we use is the size, right? So, and it must be well graded. So, if the size, the minimum size of the aggregate is 4.75 millimeter, we call it coarse aggregate, but it can go up to 80 millimeter depending upon the type of concrete that we use. So we have a well graded coarse aggregate, and for sand also we have 4.75 millimeter down, and there are gradations of different sand particle size. They must be also well graded. Now this shape actually also dictates the strength of the final product, which is concrete. Now you can appreciate that if you have a circular shape and we have sharp edges, obviously because of the presence of these sharp edges, it offers more locking with other aggregates, and obviously this shape is better than this one. Okay, so that's why particle shape is also important. So when you use gravel, round smooth surface gravels are not preferred, rather these type of gravels and stone chips are preferred when we prepare concrete. Now, the final product is what we use in reinforced concrete, and their stability of this material at high temperature is also extremely important because we have different use of cement concrete in the industry. In fact, for normal structure also, the temperature from winter to summer varies over a wider range, and obviously the thermal expansion of these materials should not be very high so that it can initiate cracking. That's why this property is so important. At the same time, the moment we introduce cement slurry which has water, it should not actually chemically react with them, and that may create corrosion of the concrete with time. So it should have chemical stability also. And finally, because this is a mass material that we use, for that cost of the material is also important. So we cannot use a costly material for regular constructions. Okay, now comes the next important component is water. Water is first used to prepare the concrete. We mix water with cement and aggregate, and the water cement ratio is extremely important because that not only dictates the final strength, it also dictates another important property called workability. So the pH value of this water should not be less than 6. Now, Seawater is not normally preferred in concrete. The reason is it has salt and other chemicals that may react with the components of concrete, and with time it can lead to corrosion. Now, water is not only used for preparing the concrete, it is not only mixed with cement and aggregate, it is also used for curing up to 28 days. Right. That's the reason we should have water with adequate quality so that it should not interact adversely with the components of concrete, and that can lead to chemical corrosion. And that's why the quality of your water is so important. Now finally, when we mix cement, aggregate and water, we get cement concrete. So what is the properties of concrete? The first property that we use in the design is its strength, and it is defined as M, then a number, say we have 20. M stands for mix. We have a mix of cement, gravel and water. And this value after M, it actually dictates the strength of the concrete. In this case, it is 20 Newton per millimeter square. Now, when we mention this strength, we actually refer to the 28 days strength. So what we do? We first prepare the concrete, pour it within the formwork, then leave it for 28 days with proper curing. Then at the end of 28 days, if we take the sample from the batching plant and then test it with same curing process, then the strength at the end of 28 days we get is the strength of the concrete that we use in design. Now, in this design, we will use IS 456-2000, and there a specific definition of concrete strength is given. For that, what you have to do at the end of 28 days, we have to test 15 centimeter cube of concrete in lab, and then only 5% of the test result is allowed to fall below this value, right? So that is the definition given in the code which we are going to use in our design. Now, the next property of concrete that is extremely important is its durability. What we mean by durability? It is the property by virtue of which concrete is capable of resisting disintegration and decay. Because once we construct concrete, say for example normal house, we expect the concrete to be there performing satisfactorily over a design life. Say for example 75 years is the design life of the structure. So over this time period, the concrete is expected to offer the design strength, and that's why this durability property is so important. Next is workability. Now, what is workability? When we first prepare concrete by mixing water with cement and aggregates, then it's a flowing mass, right? Now, that flow characteristics actually help us to handle the concrete, mix it properly, then transport it from the batching plant to the site where we have the formwork. Then we place the concrete and then we compact it. All this process is normally carried out within that initial phase I told you at the very beginning. And during this period, this workability property is so important, right? Now, when we prepare this concrete, we can go for nominal mix or design mix, that I will come in a minute. And there is a very specific code for that if we design the concrete to achieve a particular strength. Okay. Now, what are the different tests for durability, for workability? We have most commonly used test is slump test. Then we have compacting factor test. Then we have VB test, and then vibro workability test. Out of that, slump test is commonly used in every construction site. So what is done is that cone, a truncated cone, as you can see here, is filled up with concrete in 3 different layers. So this is the specific size of the cone used for slump test. Now it is actually filled in 3 different layers. So it is having a height of 300 millimeter. So every 100 millimeter is actually filled. So it is filled in 3 layers. After every layer is poured, 25 times it is compacted using a damming rod, and then next layer is filled up, again compacted 25 times, and then final layer is poured. Once it is poured, and then this cone is actually removed, and then the height of the slump is actually measured. So initially it was having a height of 300 millimeter, that is the height of the cone. Then once the cone is removed, then the concrete actually settles down, and then this height is measured, and this height dictates the type of concrete in terms of workability. Now sometimes what happens, the moment you remove this cone, it can form a bulge. Sometimes it can have a different types of failure, like this is called shear slump. In that case, middle height of the shear slump phase is actually considered the height measured in the slump test. So this is a very common test often used at construction site to check the workability. Very easy to check, and with the help of this height, the workability of the concrete is checked, and there are some codal provisions based on this height, whether we have workable concrete, and if it is, to what extent is governed by this height, right? Okay. So now again, we'll not go into the details, further details of these different tests, because this is not the material course. Here we just need to know different properties, and ultimately we need this strength value to go for our design. The final property of the concrete is again economy, because cost of construction actually matters, and that's the reason economy is also equally important. But again, for the time being, we are not worried of economy, and in fact these are the properties. For the time being, we are not worried. We are only worried of this strength of the concrete. Now when we say concrete, it has a certain ratio of cement, aggregate and water they are used to prepare the concrete. So the first components which are mixed are cement, sand and gravel, right? And those proportions are actually designed, and that is called mixed design of concrete. Now there are different options. There are actually 2 different mixes. One is called nominal mix and another is called design mix. So what is the difference between them? Normally for mass concrete, we do not design the proportions of different materials in concrete every time, and if the strength is below M20, then we can use what is called nominal mix. For example, if we use 1:2:4, the first one is the amount of cement we use, second one is the amount of sand we use, and the third one is the amount of gravel. So this is cement, the next is sand, and the next is gravel. Then if we mix it and add water, prepare a mass concrete, we get a strength of M15. Likewise, if we have 1:3:6, the concrete that we get is M10. If we change the proportion to 1:1.5, is to 3, we get a strength of M20. So these are mass concrete used for construction, and for them we can use this predefined proportion, and we don't need to go for rechecking their strength, because if we strictly follow these proportions, we get the desired strength, as you can see on your screen. Now, beyond this M20, we cannot use any nominal mix, and for that we have to go for a design mix. That means we have to design the proportion of different components, and not only proportions, also the water cement ratio, and thereby we need to design the concrete proportions, and the main objective is to achieve the final strength that we use. For example, if you use M40 concrete, for that we have to design the mixed proportions as per codal provisions, and the code for this purpose is IS 102622019. So this is the code that we should follow for this mixed design, and it has complete guidelines. So accordingly, we need to prepare the concrete, then test it, make sure that the design strength is achieved, and for that a complete set of statistical procedure is defined in that code to achieve that final goal. Again, in this course we will not go into the details of those design mix proportions. That is a separate course altogether. But what we need to know is that in Indian codal provisions we have different grades of concretes, and up to M20 concrete we can go for nominal mix, and beyond that we have to go for design mix. And I will come to that point again when we will go for design. But for the time being, this information is sufficient enough that if we go beyond M20, we have to also design not only the reinforced concrete structure, but also the concrete that we use, and that mixed proportion must follow the guidelines of the code mentioned here. Okay, so now coming back to our RCC. So for this design, we follow a code IS 456-2000. Now, as I said, the main property that we are worried in concrete design is the strength. And when we say strength, it is the strength that we get at the end of 28 days. So if it is, say, M30, so this is the value of the strength at the end of 28 days, and there is a statistical definition provided in this code that only 5% of the test result is allowed to fall below this value when we test a cube of size 15 centimeter. Right. Now, this value is called FCK value. So, for M30 concrete, the FCK, the characteristic strength of the concrete, is 30 Newton per millimeter square. Now, this is the strength that we get from cube test. So, if we use the same concrete against flexure, we use this FCR value, which is 0.7 square root of FCK. This is provided in this code. We'll also go through this code maybe in our next class as we start designing the structure. But for the time being, the point to be noted here is the characteristic strength of the concrete at the end of 28 days. Then we have the flexural strength of the concrete, and then Young's modulus of the concrete, which is EC, and the value of EC is 5000 square root of FCK. Now, code specifies that this value of Young's modulus, which is in Newton per millimeter square, it is allowed to vary plus minus 20% from the actual value. Because every time we cannot take samples from the site and then just check this Young's modulus value. So that's the reason we actually start with this characteristic strength and then convert that characteristic strength into Young's modulus using this expression. Obviously, it has some amount of uncertainty within this estimation, As you can see here, it is plus minus 20%. But in our design process, we will use this 5000 square root of FCK value as the Young's modulus of the concrete. So for design, these are the three values that we are worried of when we deal with reinforced concrete design. Now beyond that, there are two main properties of concrete that we also need to incorporate in our design. As we go through the details of design, you'll see we'll come back to these properties. What are they? The first one is shrinkage of concrete. So what is shrinkage of concrete? Recall, when we prepare concrete, we mix water with cement, sand and gravel. Then gradually we allow the water to die out, right? So the moment the volume of water is dried out with time, then what happens? Obviously there is a shrinking of volume. So this natural reduction of volume over time due to the loss of water is what is called the shrinkage. Now obviously it can cause internal stresses to develop, and when we design a structure, we have to deal with this internal stress due to shrinkage. Otherwise, it may lead to crack of concrete, right? So that's why it is so important. Now, another property is what is called creep. Now, what is creep? It is a slow process, but it's a continuous deformation over time due to chemical rearrangement internally, and it takes place due to the constant loading of the external loading on the concrete that we pour within the formwork. Just imagine if there is a formwork, very often we encounter at construction site, all of you have noticed. Now, once this concrete is poured, because of its own weight over time, also it deforms, and because of the chemical arrangements, because if you recall, cements are nothing but different chemicals that react with water, which produces heat of hydrations. So this chemical rearrangement internally also produces kind of internal stress, that is what is called creep. So both of them may be detrimental for concrete because both of them can develop internal cracks if not properly designed, and that's why in our design process we have to take care of these two properties of concrete. The first one is due to loss of moisture over time, which causes a tensile strength within the concrete, and then creep, which is because of external loading, a constant loading. The deformation that takes place over time is what is called creep. So with that basic introduction to reinforced concrete as a material, let us stop our lecture today here. In our next class, we'll use this material property and we'll see how we can use this material property in our reinforced concrete design. That we'll discuss in our next class. So with that, let us close here, go through this class notes. If you have any doubt, do let us know. We'll definitely clear your doubts. Thank you very much.